So I'm going to talk about knot invariance and quantum field theory, but I need to give you a little background about how these knot invariants were invented or discovered by knot theorists before I bring in the physical ideas. And so this is a very uh, interesting historical point that I'm making here. Um, there's a book by Romilly Allen. Of course, this isn't how they were discovered, but it's an interesting historical point. There's a book by Romilly Allen on Celtic art, as you see here. This was published around 1900. And in that domain, people think about making designs like the Celtic designs that you see over here on the cover of the book. And Allen points out that the designs can be obtained, and he conjectures that they were obtained by people starting with very regular rectilinear weaves, like the one that is illustrated on the right-hand page, and then applying some changes to those weaves to get to the patterns that are traditional in Celtic art. And the changes that he suggests are that at a given crossing in the diagram, in this weaving diagram, that it is, you think of erasing the crossing and reconnecting the lines, either reconnecting them so that they are in parallel vertically or reconnecting them so that they are in parallel horizontally. And then if you look at the designs, you see, oh, yes, indeed, it's true that you can do that. And in fact, in more modern times, one finds on the web programs about Celtic knots, which have initial points like this. And I won't demonstrate a program. I could if I wanted to look it up on the web and show it to you. But the program acts on an initial graphic like this. And if you put your mouse on the crossing and press, it will smooth the crossing, putting it into that form that I told you, parallel lines, vertical or horizontal. Press it once, hit horizontal, press it another time vertical, and then you can try out various patterns that you like until you find one that you happen to like. But Romilly Allen, writing in 1900, didn't have such programs, but he suggested that that was the method by which the Celtic patterns are produced. So now jumping up to around 1983 or 4, there's an example, right, from here to here. That's not the jump I meant, but jumping up to 1983 or in 1984, when we knot theorists were starting to realize that there was a lot more we could do with diagrams than we thought we could before. And this was partly the result of, this is a formula of mine, but this is partly the result of very much influenced by von Jones, who discovered a new knot invariant, and he discovered it by thinking about statistical physics. I won't go into how he discovered that knot invariant, but it inspired knot theorists to start looking at what you could do with the diagrams that hadn't been done before. And this, although it is in its way a direct descendant of Romilly Allen's picture on that book, was an entirely new idea for us. The idea, of course, is not one that Romilly Allen would have followed. I'm saying here implicitly that you are going to have a function on the diagrams of knots which takes a given diagram and writes it as a sum of evaluations of two related diagrams, and the two related diagrams are obtained by smoothing the crossings in the two possible ways. This is an analog of a kind of expansion for graphs in graph theory called the Tut polynomial, where you delete or contract an edge in the graph. And here, this is the analog of deletion and contraction, although in this case, it's reconnection in the two possible ways. And then it does indeed turn out that that this leads to a new invariant, and surprisingly, for me at the time when I discovered this, the Jones polynomial itself is what comes out of this particular thought experiment in diagrams. So well, in any case, you do get a non-invariant, and the way you see you can get a non-invariant is to analyze what happens to this procedure when you look at a move on the knot diagrams. And by a move on the knot diagrams, I mean this kind of thing here. You see one line goes over another twice and another goes underneath. And if that was a bit of rope, you could pull it apart. So you would like it to be the case that this calculation would be the same, would give you the same result as this one, where they're pulled, I'm sorry, this one, where they're pulled apart. You can see my pointer, right? Is it true that you can see my pointer?
Yes, we can.
Good. Okay. Yes. So one would like it to be the case that this would give you the same evaluation as this when you expand it according to the formula. Well, so you do the exercise, you see, you expand it according to the formula. The formula says that you'll multiply by A, one, and the other by B. If there are two crossings, that means there would be four ways of smoothing the crossing, and they would be multiplied by A, B, and AA, and so on, and collect terms and find out that that means that it would be good if you decided that this one was 0 and this one was 1. So you decide that. You say, all right, that means that the value of a loop was going to be such that this vanishes, and that B is equal to A inverse. And then you find that it's invariant under another important motion on diagrams, which is sliding. You have one arc which is going twice underneath another, and these cross over, and you could slide that arc down a little bit to here. And it turns out that a little bit of calculation here shows that indeed that will work. In fact, this is so amusing, I can't resist showing it to you. Let's just look at it. I'm going to magnify it a little bit so you can see it better. There. In this case, we already set it up so that it would be invariant under the 2 move. And we expand on this crossing, bingo. And then you see there is a 2 move. And so it's invariant under the 2 move. It can be slid all the way down to here. And this one doesn't matter. It's just the form of things. And then you see this has exactly the form of having been expanded above. So expanded below turns into expanded above, and it's invariant under that move as well. And so by these elementary manipulations, one can adjust that polynomial in A and B and loop value D so that it's invariant under moves that are needed in order to make it a not invariant. And that ends up producing a really important new and not invariant, which is extremely elementary. Could have been invented in Romilly Allen's time if someone had had that idea then. And it's related to statistical mechanics in the following graphical sense, that the invariant can be thought of as a sum over different states of the graph. Here's the graph of the knot. And you smooth it in the 2 different ways, and you will get 8 different ways of smoothing that guy. And thus it's like the different states in a statistical mechanics expansion. So, so these invariants, of which this is a nice example, turn out to be related to combinatorial statistical mechanics, and they are in fact directly related in various ways that I'm not going to go into. So that's the picture of what knot theory had broken into around 1983-4. And then the question arose, pushed rather hard by Michael Atiyah, is shouldn't there be a quantum field theory interpretation of these ideas, statistical mechanics, combinatorial statistical mechanics? Why shouldn't there be some field theoretic way of thinking about these things? And eventually, this question was answered very beautifully by Edward Witan. And that's what I'm going to tell you about. And in order to do that, I have to jump to a different place in this slideshow. Just a moment. Sorry about going way past a whole bunch of things. Right. So this is Witan's paper. And I'll just begin telling you about what he did here. So actually, this is a little quote from the paper, and it will do as a first pass. He's going to look at gauge fields on three-dimensional space, and he's going to evaluate the knots or knot components. In this case, it's written so that the CIs are the components of some link. And each link component is going to be evaluated by a Wilson loop. Wilson loop means that you think of the gauge field. I say gauge field. I should really say gauge connection. In any case, it is the generalization of a potential function, a vector potential. And as you know, if you differentiate a vector potential in the case of electromagnetic theory, you get the field. So if we're thinking of the physical field, you need to take the curvature of the connection. I'll explain in more detail in a moment. But since it is a connection, that means it tells you how to parallel translate. And consequently, you can take a point on the knot and imagine a particle for that particular kind of gauge theory that you translate around the knot until you come back to where you started. And then it has a different internal vector from the one where it started. And you measure that by taking the trace. So that's the holonomy. And you measure the holonomy for the knot. And the holonomy for the knot in the field is not an invariant, but it's getting close to being an invariant in some ways. And if you average over all the fields, then you do get the not invariant. And so the averaging over all the fields is a gauge theoretic functional integral. And that's what Witan's solution was, that you can think of it in a quantum field theoretic sense by taking an appropriate gauge theoretic functional integral. And the exponential IL, that's the Lagrangian in this case. And I'll be telling you what Lagrangian you choose. So that's how these non-invariants went from being strictly combinatorial diagrammatic or analogs to combinatorial statistical mechanics to being understood in a quantum field theoretic framework. Now, in this slideshow, I went through, and you can read it when I give you the slideshow. I went through a little history about Feynman's path integral and how he got to it, and some quotes from his Nobel lecture. And while I don't want to do all of that, some of it is fun. So let me just tell you a little bit. As you know, the Lagrangian is in most situations is the kinetic energy minus the potential energy, and classical mechanics comes from extremizing the integral of the Lagrangian over paths from A to B. And what Feynman discovered was that if you take e to the I Lagrangian over h bar and integrate that over all paths, you get the amplitude for the quantum wave function. You get a solution to Schrodinger's equation. That was his discovery, and that was the technique by which he, related to that are all the techniques that he discovered for doing quantum electrodynamics. So he, in his Nobel lecture, he recounted how he discovered that. And let me see if I can find the question. So, as he says, and I don't want to read everything here, he was searching for a way of formulating quantum mechanics that used the Lagrangian. And he was struggling with that problem. And he went to a beer party, and now I'll read. I went to a beer party in the Nassau Tavern in Princeton. There was a gentleman newly arrived from Europe, Herbert Yela, who came and sat next to me. Europeans are much more serious than we are in America because they think that a good place to discuss intellectual matters is a beer party. So he sat by me and asked, "What are you doing?" and so on. And I said, "I'm drinking beer." And then I realized that he wanted to know what work I was doing. And I told him I was struggling with this problem. And I simply turned to him and said, "Listen, do you know any way of doing quantum mechanics starting with action, where the action integral comes into the quantum mechanics?" "No, but Dirac has a paper in which the Lagrangian at least comes into quantum mechanics. I'll show it to you tomorrow." So the next day we went to the library, and they have little rooms. And we went off, and Dirac said, "There is in quantum mechanics an important quantity which carries the wave function from one time to another." And in Dirac's version, it uses the Lagrangian, and Dirac said that his quantity was analogous to using the Lagrangian. Yela showed me this and read it, and I read it. And he explained it to me, and I said, "What does he mean they're analogous? What does that mean, analogous? What's the use of that?" He said, "You Americans, you always want to find a use for everything." I said that I thought Dirac must mean that they were equal. "No," he explained, "it doesn't mean they're equal." "Well," I said, "let's see what happens if we make them equal." So I simply put them equal, taking the simplest example where the Lagrangian is the 1/2 mv squared minus v of x, but soon found that I had put a constant of proportionality in, suitably adjusted, wrote the integral across a small path, and calculated with a Taylor series, and out came the Schrodinger equation. So I turned to Professor Yela and said, "Well, you see, Professor Dirac meant they were proportional." Yela's eyes were bugging out. He'd taken out a little notebook and was rapidly copying it down and said, "No, this is an important discovery. You Americans are always trying to find out how something can be used. That's a good way to discover things." And that's Feynman's description of his discovery of this, that you integrate over all paths from A to B of e to the IA over h bar times the integral of the Lagrangian, the action. And that's the advent of path integrals into physics in that form. And then I won't go through it, but if you look at Feynman, you probably are likely to have been over various derivations of this sort of thing anyway, but if you want to see how it appears in his thesis, I put it into the slideshow. And I think that the way it appears in his thesis is pretty much the way he describes having done it on the blackboard with Professor Yela. It's quite elementary and direct. He does exactly what he said. He expands it into Taylor series, uses some Gaussian integrals, and out comes a piece that indeed is a solution to Schrodinger's equation. But as I said, I do not want to drag you through that. There is the question of what do we mean by the integral? And you'll see that in the case of the sort of integrals that I'm talking about, if you were to look around in the literature, it's still the case that no one knows how to define it in the sense of measure theory. And on the other hand, when one just works with these as though they were numerical and did have a value, and then attempts to adjust them so that they are numerical and do have a value. This doesn't satisfy mathematicians, but it works fine in lots of mathematical physical situations. And when I'm doing these things in a few minutes, you'll see that really the only thing I'm doing is integration by parts. That I'm saying that if I have two functions and their difference is a derivative, then the integrals that I'm using will be equal because I'm assuming things vanish out there in infinity or go to zero out there at infinity. So that means that lets you deduce various things. For example, if you if you shifted your function by a constant, well, then all the rest of the Taylor series is involving powers of that constant. So as far as integration is concerned, they would be the same. And so I could think, if I want to make a miniature theory of this, that I will talk about equivalence classes of functions under the equivalence relation, that differences that are derivatives are equivalent, just like you do in elementary calculus. And then you can calculate lots of things without knowing that your integrals actually exist in the usual mathematical sense. So you can think that way if you wish. Anyway, here's the Witan integral, and I want to show you a little bit about its nuts and bolts. So I've just repeated what I said before. There is an exponentiated Lagrangian, which I've written as S of MA. M would be a three-manifold, but it might as well be ordinary three-dimensional space. And WK is the Wilson loop. Now, the thing that I'm integrating, the Lagrangian, is a certain three form, which has this form for the gauge field. And I'm about to tell you definitions of things. A gauge field depends on a Lie group, Lie algebra. And this Chern-Simons form, which takes the form of the Lagrangian, is a three form, differential three form, and it is A wedge dA plus 2/3 A wedge A. If you were to take D of that, you would see that it is up to some term which would integrate away in 4 space, F wedge F, where F is the curvature of the gauge field. And I remind you, and we'll be explaining in a moment, why the curvature of the field is dA plus A wedge A. And that's what gives you the physical field. So we'll be going back over this in a moment. But I'm just giving this to you in detail, and then a little more detail, and then a little more detail. So here's the special weighting factor involving the Chern-Simons Lagrangian. That S of MA is the integral over 3 space of the trace of the Chern-Simons form. And this is the Wilson loop. So the Wilson loop is usually expressed in this way, that you think of integrating around the knot, the field, the gauge field, and you exponentiate that. And in order to make sense out of that, you need to have an order along which you go, because you're going along the knot in a certain order, and the terms in this gauge field are not commutative. We'll see how to handle that in a moment. But that's the nice formula of Witan, that is supposed to give us an invariant of knots inside the manifold. How does Witan know that he's getting an invariant of knots? Well, I'm going to be showing you some nuts and bolts of that, but they're not in his paper. I think he knows, because the kind of calculation that I'm about to show you is like 2 plus 2 is equal to 4 for him on the one hand, and also he's looking at it and saying it's metric independent. The Lagrangian that's been chosen is metric independent. And if we were to integrate over all those fields something that's metric independent, it ought to be merely topological. But there is the technical matter of, well, how do you see directly that when you push the curve around, you get something that doesn't matter, that is invariant, like I was verifying in my diagrams that my adjusted statistical mechanics sum was going to be invariant under pushing it around by those moves. So I would like to see it at that nuts and bolts level. Here's what the Chern-Simons Lagrangian looks like. I still haven't told you what a gauge field looks like, but I'll get to that in a moment. As I say, it's a Lie algebra valued 3 form, so a Lie algebra valued 1 form, so we could open it up and see Lie algebra in it. But if you didn't do that and just took D of it, you see, you would be getting partial derivatives of the field like this, you see, and then you're recognizing that that looks like the electromagnetic field if this was a vector potential. But there are also other terms involved, like commutators of the AIs, because of the fact that we're wedging here. And so this is looking like A wedge dA. And there's a funny 2/3 in there, but you're seeing that the curvature is floating in there in a certain sense. Now, what does the gauge field actually look like? Well, it looks like this. We have dx1, dx2, and dx3, the three directions of space, infinitesimal space directions. We have a collection of matrices, T1, T2 out to Tn, which are a basis for Lie algebra. So you might have Pauli matrices if you were doing SO3. And you have some functions that are dependent upon the two indices of Lie algebra and space. So these are the actual potentials. This is the Lie algebra there for the gauge symmetry, and this is the X. And this is a Lie algebra valued one form. And I can pack it back up in various ways. I may eliminate the index A, and then I have just A upper K, and A upper K means A upper K sub A TA summed on A. That's the gauge field or the gauge connection. And now some diagrams that I use. Not anybody else's diagrams, but to some extent these diagrams are this kind of diagrammatic is often used these days more than it was when we started this back in the 80s. The idea is if you have a linear transformation or a matrix, then you may write it as a box, and it has some indices. Like here's an index for this matrix, which is just label, right? It's just the label. There's T1, there's T2, there's T3, like the Pauli matrices, sigma 1, sigma 2, sigma 3. Then there's the fact that it's a matrix and it has indices ij. And the indexes I and j in a matrix indicate source and target, right? They indicate domain and codomain, home vector space and target vector space. And so you can think of them as corresponding to the arrow in the line which goes between the two vector spaces, but now they're going to be recipients of an index. So this is the I and the j, and you might write T upper A sub ij. So I use a box like that for a matrix. And then if you were to multiply two matrices together, you stick their boxes together, and you have a little, I should have had a slide for this. You stick their boxes together, and went along the line bit where they join, you have to sum over the indices for that line. Because remember how you multiply matrices? Mij times Mjk represents the product of M and another N, Mij, N, Jk. You sum over the common J, of course. So if that J would be labeling a line which had its ends in one box and the other box. So that's matrix diagrammatics. Here's the Wilson loop. And now comes, this is very important. In order to understand what's meant by integrating the field around the knot, I rewrite it, and I could just do this formally with you. E to the something is 1 plus that something. A is infinitesimal, and so e to an infinitesimal is just 1 plus the infinitesimal, and the rest of the series is gone. So at every point, e to the a is just 1 plus a, which I've written out. And then the order, well, you have to take the product all the way along the line from beginning to end, and it's a knot, and you go along the knot in that order until you come back to where you started, and you take that product. And then you should have taken a trace, which I have forgotten to write here. But let's just say that the product over points along the knot of matrices means the trace, all right? And we won't worry about writing the trace into this slide. But now if you look at this again, you realize, oh, actually what this means is if I were to apply it to some vector, where is this vector? I wrote the gauge field here. But the gauge field is a matrix valued thing and acts on vectors, right? Each of these TAs is acting on some vector. So you could act this whole thing on a vector, and it would give you a new vector after you had gone all the way around the knot. But think of it 1 bit by 1 bit by 1 bit. You started out with some vector over here, and then you moved slightly infinitesimally forward, and you got multiplied by 1 plus a. So you ended up being v plus a times v. And a represents parallel translating in the sense of this kind of differential geometry by one small step. So a is a connection. And this expression here is telling you what happens if you apply the connection continuously, parallel translating all the way around the knot until you got back to where you started. So we went from exponentiating to finding the 1 plus a to understanding that successive multiplication by 1 plus a is in fact parallel translation. And so this is the holonomy of moving corresponding to moving a vector all the way around the knot until it comes back to where it started. And I have much more to say about that in a moment. The other bit of nuts and bolts that I need is the possibility of taking one of these matrices and sticking it into the line. That is, I think of the line, the Wilson line, the Wilson loop, as this product of matrices going all the way around until I come back to where I started. And having bit my tail, I'm taking a trace. But I could, somewhere in the middle, insert a matrix if I felt like it, and I'll show you why I want to. So I could insert a matrix somewhere, and then what would that mean? That would mean that I would do all this, and I bump into this matrix at a certain point, and I insert it into the product, ordered product, going all the way around, and I come back. So I have a kind of special advanced calculus kind of operation that I can do here, which is insert a matrix somewhere in the line. It's useful to be able to do that, and it has to happen sometimes, as you'll see. So then the slide has a moral here, which I might read. Think of the vector on the line. As the base of the vector moves by dx, the vector changes to 1 plus av. And this is the analog of parallel translation. I already said it, but there it is. So there are a couple of things in this slide. I'm taking my time with it. One is diagrammatic representation of matrices. The other is that the holonomy amounts to parallel translation. And using diagrammatic representation of matrices to insert matrices into the loops. So here we are, and this repeats what I said before, but now I need one more operation that's going to happen quite a bit, and that is functional differentiation of the loop or other things with respect to the coordinates, the coordinate functions of the gauge field. So that means that we are thinking of the coordinate functions of the gauge field as variables. Now, that means that you have an infinite collection of variables. And of course you can do this. This is what you do when you're doing functional differentiation. It involves using delta functions, and I will most of the time point out the formal result without worrying about the delta functions. Let's consider what happens when I differentiate a Wilson loop with respect to this A upper A sub k. Now, I'm sure I have a better slide of this in a moment. Let me check. Oh, all right. Then we'll have to do it in our heads, but it's not hard. I have the Wilson loop over here, and I want to differentiate it with respect to A upper A sub k of x, and that means a specific x. Every x, there are infinitely many x's, but I'm talking about some very specific location in space. And that means that only one term in this product is affected by that differentiation, because this is a variable. Every single one of these is a different variable. So if you differentiate with respect to this variable, which is staring you in the face, it will go away. The one will go away, and you'll be left with ta dxi. That's it, just that. The rest of it's gone. So this entity in parenthesis gets replaced by just TA dxi. And all the rest of the Wilson loop remains exactly the same. That's the yoga of differentiating with respect to the gauge. And so it is an insertion of a matrix into the Wilson loop. It is an insertion of TA into the Wilson loop and the dxk, which I've written as a little line on a triangle, the dxk, in order to have diagrams for everything. I want diagrams for everything because I do. And so this is the formula for differentiating the Wilson loop with respect to the gauge. Okay? It's very simple, but I know there are a lot of conventions here. It's just that when you look at the gauge product, when you look at the Wilson loop, you see a 1 plus A in here. And if you're differentiating that with respect to one of its coordinates, then the coordinate disappears and you're left just with a matrix. And you insert that matrix. I need another diagram, and then I think I've told you my lexicon of diagrams. My other diagram is an epsilon. It's a trivalent vertex, simple enough graphical thing. Trivalent vertex with labels on it, I, J, and K. But I interpret it as epsilon I, J, K. Epsilon I, J, K is a little tensor, which is equal to 1 or minus 1 or 0. It's equal to 1 if ijk is a sine 1 permutation of ijk. So for example, epsilon 1, 2, 3 is 1. It's equal to minus 1 if the permutation has negative sign. For example, epsilon 2, 1, 3 is minus 1. And if two indices are equal, it's 0. So epsilon figures in defining vector cross products, curls, and all such things. And then it turns out, and this I shall not prove, that the derivative of the Chern-Simons Lagrangian is the curvature. And the curvature coefficients are the coefficients of dA plus A wedge A. I'll say a little more about curvature, but that's what it turns out to be, only not quite. You have to switch the indices around, and that's what epsilon does for you. So you need to tie in this index into an epsilon. You get two indices out for one index in. Like if this was 1, then this could be 2 and 3, or 3 and 2. And the upper index is the A. And the A is the Lie algebra, and the K is space. So these are space indices, and this is Lie algebra index. Space and Lie algebra indices on the curvature tensor. So I need those. Now what about curvature? Curvature, as I said, is dA plus A wedge A. And what I've said is that differentiating L with respect to A yields curvature with these nuts and bolts. Now what about curvature? Let's take a digression and talk about the curvature. I know I'm over time, but I will try to finish after 1 hour, and then that leaves us some time to discuss. I mean, 1 hour from when I started, okay? Here's our gauge field, which written out looks like this and packed up partly looks like this. So I'll pack it up to this position, right, where it has some dx stuff in it. And now I want to think about its properties under parallel translation, and then you'll see that everything works the way it's advertised. I wish to parallel translate around a small rectangle, so I'm going to parallel this way and then up this way. Or I'm going to parallel around the other two sides of the rectangle, and I'm going to compare the two results. I hope this part is feeling quite familiar to you. I'm sure you've seen this kind of calculation before. So I'm going to do 1 plus A to get to here, and then I'm going to do 1 plus A again, but I'm doing it from A at x plus dx, right? So that gets expanded into A of x plus partials of AI dxi, right? Because that's what it is. A plus x plus A at x plus dxi is expanded like that. And then I multiply it out, and I get a certain form with some terms. And I do it around the other side, and I get a certain form with some terms. They're both on this slide. And then I take the difference to see what happened as I went around the rectangle. And when you take the difference, a lot of things disappear, but some things that had to do with the order in which you went remain. I have an ith partial of AJ in the first one, and I have a jth partial of AI in the second one. And I have the product of AK with AL, they're matrices, remember? These guys are matrices. And I have the product of AL with AK in the other one. And consequently, I have to look at a commutator when I take the difference between them. And so what I end up with is DIAJ minus DJAI plus the commutator of AI with AJ. And that is the generalization of the field that corresponds to the curvature of a gauge field. And that is what is regarded as the physical field. If you had an ordinary vector potential, then these commutators would go away, and this would be the formula for the electromagnetic field. So that's why I was going on and on about curvature. That's the formula. And if you're thinking in terms of differential forms, well, then that formula comes out neatly like this, dA plus A wedge A, because in differential forms, dxi, dxj is minus dxj, dxi, and so you pack it up by summing over I less than j, and you get the differences, and so the commutator comes back in, and you get exactly that. So one can say concisely that the curvature is dA plus A with J, and that's the physical field. The other thing is, what is this Chern-Simons form? It's worth looking at this for a moment just to get the context. If you take F wedge F and multiply it out, you see that you get something. You get this form, and if you take D of the Chern-Simons form, you get most of this form. Sorry, that's a little technical. Maybe I shouldn't have done this, but let's just slow down and look at it, right? F wedge F, there it is. You get a certain form. If you take D of Chern-Simons, then you get dA wedge dA, just like you did here. And you get, there's this 2/3, and the 2/3 runs you across this sum of dA and dA and dA added up. And so you, if you then compare with what happens, you find that if you are integrating over 3 space, the Chern-Simons form, of course, by Stokes' theorem, that will be the integral over d4 if it was defined on d4 of d of it, and that turns out to be F wedge F. So Chern-Simons is related to F wedge F. And this is the beginning of what Chern and Simons were doing, getting at curvature by way of differential forms in a larger system of thought. And that's how Witan comes to know about this, I'm sure. In any case, this is where we are. Now, I want to talk about the topological invariant. I've set up all these different pieces, and I want to put them back together and show you how it ends up being topologically invariant. So what is it I want to examine? I want to examine how the Wilson loop changes if I push the knot line a little bit. So I look at the Wilson loop for a knot line where I pushed it a little bit minus the Wilson loop with no push. And now we understand immediately that there isn't any hope in this being an invariant as it stands, because we're doing differential geometry here. And if you go around a little tiny loop, you take the holonomy around a little tiny loop, and that's the difference between this one and this one, going around a little tiny loop, then the answer in standard differential geometry, of which this is a generalization, is that you get the curvature of the field. the curvature of the field. That's what we just worked out, right? That's why I decided to go through it carefully. If we go around a little infinitesimal rectangle or an infinitesimal loop, then we pick up the curvature times dx, times a little bit of area form. And then it's tied in with the Lie algebra, of course, which I left under the hood when I did that calculation before. So what happens is that the Lie algebra matrix gets inserted into the line, insertion again, and then tied into the curvature like that. So while we don't know while we know that the Wilson line is not an invariant, it will vary according to the curvature of the field, which means that when you push it around, it depends on how the field strengths are at that particular place in space. If the field had zero curvature, then you would be getting some topological invariance, and that's important, but we're not going to discuss that end of things. So now what we want to see is what happens when we do Witan's integral. So I'm going to put everything together and show you how it looks like if I do the variation using Witan's integral. And this is the advantage of the diagrammatic notation, that I can say this whole argument in one slide without any symbols other than the diagrams. Advantage for me, I hope it might be an advantage for you. Let's see. Let's try to walk through this. So I have varied the Wilson loop topologically, which meant that I inserted curvature into the loop. That is, I have the curvature tensor, I have two space dxi, dxj's tied in, and the matrix, the Lie algebra matrix, is sticking inside the loop. So that we happen to know that the curvature is dl, remember? And there's an epsilon now, dl. And now we're going to see how the integration process invokes L enfolds L into its workings, because I have dl here. And so I might as well say d of e to the kl. I've written this as just a k. D of e to the kl, so I need to multiply by 1 over k. And now I'm differentiating this factor. This is a product of two factors, right? The exponentiated Lagrangian factor and the Wilson loop factor. But now the derivative is on the exponentiated Lagrangian. Now I do integration by parts. Change sign, put the integral back over on the Wilson loop. Now I'm differentiating the Wilson loop. But you remember that differentiating the Wilson loop causes the insertion of a bit of Lie algebra and a dx into the Wilson loop, coming from this index up here and that one down there. And that these were space indices, and that's where the dx connected in. And this is where the Lie algebra index connected in, but it was already connected to a Lie algebra element. And so you have a Lie algebra element connected to a Lie algebra element, two insertions on the line. We could worry about the geometry of that. But the dx part is separated into an extra little tensor over here. And that little tensor is an epsilon I jk dxi dxj dxk. That's a volume form. It will vanish unless the directions of dxi, dxj, and dxk form a three-dimensional frame, or linearly independent. And so you see that the integration process against the Chern-Simons Lagrangian, and the fact that it's related to curvature, and that the Wilson loop produces curvature when you deform it a little bit, has switched the deformation into a bit of volume, which might happen. But if no volume happens, then this would be 0. And that says that it would be topologically the same. Now, if you go back to the kind of not diagrammatic moves that I was talking about before, the kind where you slide a bit of line along a tiny plane underneath another bit of line, and those were both of those moves that I showed you were of that type, well, then you aren't generating any volume in the movement. If you don't generate any volume in the movement, you don't generate any volume in the volume form, and it's 0. And so this is telling you that that very small deformations that are essentially planar are going to leave Witan's integral invariant. And that's sufficient because you can proceed to get from one place to another in space with curves by doing little small deformations that are basically happening in a plane, except for some little bit of curly twisting, which has to do with framing the knot. But if you ignore that, then it's invariant. That means it's a framed knot invariant. And that's what gets proved out of this argument, this part of turning it into nuts and bolts to look at the topological invariance. So that's what I wanted to show you, how one can look at this in a very elementary way and keep track of all the indices with some diagrams, which I find useful for myself, because otherwise we would have a formula, we would have a bunch of formulas here with lots and lots of indices, and it wouldn't be so easy to locate the themes of it. So when you vary the loop, the Witan integral changes by the appearance of a volume form and a double Lie algebra insertion. The double Lie algebra insertion is very interesting, but I think we won't worry about it right now. One of the things you can do with this is ask what happens if I were to switch a crossing. Then it will change, and you can figure out how it changes in relation to the Lie algebra, because there is a double Lie algebra insertion that happens that ends up not being 0 when you switch a crossing. When you make a deformation that switches a crossing, another space direction happens. One line is moving in a plane, but the line is also perpendicular. There is another piece of line that's perpendicular to that. And you go back into the calculation I showed you, and you'll see that the volume form doesn't vanish anymore because of that switch. And the Lie algebra insertions look like this. We could go into more detail about that, but I don't want to do that, nor do I want to do specific examples right now. But I do want to show you how this formalism ends up being related to the origins of what is today called loop quantum gravity. Loop quantum gravity originates from the work of Ted Jacobson and Lee Smolin and Carlo Rovelli and Abhay Ashtekar. And in the original versions, they used functional integrals to define the loop transform. Now, I'm not going to do the quantum gravity theory, but I made in this slideshow a summary of it, which occurs after this, which you might want to look at if you're interested and you get the slideshow. So the slideshow has more details than what I'm going over, but consider this. They had the following idea, that they have reformulated gravity, and this is what I'm not telling you about, a version of quantum gravity, so that there are functions of a gauge field. And the gauge field in this case is being used because they have reformulated gravity in terms of gauge fields. How, I better not try to tell you in such a short time. But now you have a quantum theory where you have functions of gauge fields. Everything I say would be at that level of generality. And they define what they call the loop transform. Now, the loop transform says phi is a function, psi is a function of A. Let's make it a function of knotted loops. So we'll integrate over all the gauge field, psi of A, Wilson loop for A, okay? Just like psi of A being the exponentiated Chern-Simons Lagrangian. That would be an example. It is an example for them. It's called the Kodama state in their theory, and turns out to be of some significance. So if you have a differential operator that's defined on these functions of gauge fields, you can use this integral transform to make it into something which does something to the Wilson loops, possibly to the knots. So delta psi hat is going to be the integral of dA delta psi. And then by my principle of integration by parts, this is the same as minus dA psi of A delta applied to the Wilson loop. And then this might be understandable. That was their idea, and they used it. And here's how it looks. oh, this is just saying what I just said. Okay. But now they have two operators, which I have indicated diagrammatically. G is called the diffeomorphism constraint, and H is called the Hamiltonian constraint. These are the two key operators that have to vanish on the psi of A in order for psi to be a state in their quantum gravity theory. So let me show you what happens when we use the formalism that I built for you and let these operators act. Here's G. I'm going to have, of course, G looks very strange, and I haven't motivated it, but you understand what it means, right? You're summing over the indices. So you have a D upper A and lower K, and you're summing F upper K lower and so on, and there's a DX. So it's just been written that way, little gadget. And I applied G to psi, and then I push it and apply G to the Wilson loop. So I'm applying this to the Wilson loop. Now, what does D do to the Wilson loop? It puts a Lie algebra element in, connecting it to the F up there, and it puts a DX, and that's connected to the F down there. We're using the same nuts and bolts I had before, right? But that's the insertion of curvature into the Wilson loop. But that's the same as deforming the Wilson loop. So this differential operator applied to their wave function transforms into deforming the Wilson loop. And that means that if the wave function is such that it gives a non-invariant, then that wave function satisfies their diffeomorphism constraint. It will have that G applied to it will be equal to 0, or at least its transform has that property, and then you need to believe that the transform has some faithful nature. So they could solve the diffeomorphism constraint for the Chern-Simons psi by invoking Witan's work. So they were able to give an example of a solution to their system of quantum gravity at that time. And the Hamiltonian constraint similarly differentiates the Wilson loop a couple of times and ends up with a peculiar Lie algebra insertion and an epsilon up here, but that one always vanishes, and that's good for them. They managed to show that the Hamiltonian constraint will be satisfied by anything they choose. And so this was the beginnings of the loop quantum gravity theory, using functional integration and connecting it partially with Witan's work. The theory then continues on in other directions because I see. All right, I don't want to do too much more. It continues on in other directions, partly because the methods of using functional integral are hard to actually implement and get numerical results out, and they wanted more geometry, and so they used other methods such as spin networks and what are called foams, and foams are combinatorial approximations to the three-dimensional space or four-dimensional space that one would then act on. And so in a certain sense, they walked back into combinatorial statistical mechanical ideas in order to continue the theory. But if you look at the literature of this theory, you'll see that some of it's still using this kind of functional integral approach, and others using combinatorial. And the people involved in this theory have been in a long discussion with other physicists about why they shouldn't be taken more seriously than they are, and they do take themselves quite seriously. You can see all this kind of discussion in Lee Smolin's book called The Trouble with Physics and his other books about philosophy of physics. But this approach is sufficiently far from string theory from their point of view so that they are in an interesting long argument with string theorists about the relationships between this and other people's attempts to do gravity and quantum gravity. So why did I tell you this long story? Well, I think it's an interesting story, but also because let's go back to some picture of the Wilson loop. Because of the fact that what we're doing here is we're looking at a knot and thinking about it from a field theoretic point of view, right? We're thinking of this knot as being embedded in a gauge field and measuring things about the knot, and we get topological information about the knot. But we are not doing the sort of thing that that John Williams has been talking about of imagining the actual physical field as bent around into the shape of a knot and thereby becoming a particle by means of its flow being entrapped in a topological form. But somehow, all of this is very close to that idea. And I thought that by telling you this story, which I happen to know from my own work, we might get some ideas about how to understand knots as particles, not just knots as knots. And while this story is close to the idea of thinking of knots in a physical space, it isn't that close to thinking of knots as particles. But maybe when you look at it through your eyes, you will see that perhaps it is close to thinking of knots as particles. So I'll stop there.